Hello, and thank you for being here. Today I'll be presenting our final project for the Data Science Lab. Our project is a deep learning-based image classification system designed to recognize American Sign Language letters from static images using transfer learning. The core goal of this project was to develop a machine learning model that could take an image of a hand sign and accurately classify which ASL letter it represented. We used a labeled ASL dataset where each class, like A, B, or C, is stored in its own folder. We chose this project because it's both technically challenging and socially impactful. Sign language recognition can help bridge communication gaps for deaf and hard of hearing individuals, especially when integrated into assistive devices or translation systems. We built our project using TensorFlow and Keras, which gave us a flexible framework for deep learning experimentation. Our main technique was transfer learning, specifically using the MobileNet V2 architecture pre-trained on the ImageNet dataset. This gave us access to a model that already knows how to detect edges, textures, and shapes, allowing us to adapt it to our ASL dataset with relatively little data and computation. So I'll just be going over our code next and explain each section of our code and what we did and how it impacted the project. So to begin with the import libraries, we imported all the essential Python libraries needed for our project. This included TensorFlow, Keras for model construction and training, NumPy for handling data structures, and Matplotlib for visualization. We also used Skitkit learns metrics like the confusion matrix and classification report to evaluate our model's performance, and OS for managing directory paths when loading data. Next, we defined our key training parameters. We resized all input images to 224 by 224 pixels. This is the standard size expected by MobileNet V2. The batch size was set to 32, which is a balanced choice for stability and speed. We also split training into two stages. The first one being an initial 10 epochs with frozen layers, and the second one being a fine-tuned phase of 20 epochs. This two-phase training strategy lets the model gradually adapt to the specifics of ASL data without forgetting what it learned from ImageNet. Since the ASL gestures can vary a lot depending on lighting, angle, and hand shape, we applied moderate data augmentation using the image data generator class. Our augmentation included random rotations, zooming, brightness shifts, and horizontal flipping, and slight translations. This helps the model generalize better and prevents it from overfitting to specific poses in our training data. Next, for loading the datasets, with augmentation configured, we loaded our dataset. We split it into a training set and validation set using an 80-20 ratio. Both were scaled down to the 0-1 range by dividing pixel values by 225. Using the flow from directory method made it easy to load images based on folder structure and class labels. Next, for the class balance check. Before training, we checked the class distribution by printing how many images each letter had. This revealed class imbalance. Some letters like X had more samples than others, and that can skew the model's predictions. Without correction, the model could end up predicting those dominant classes more frequently, regardless of input. For the class weights, we manually defined class weights. We increased the weight for underrepresented classes like A and B to 1.5 and slightly decreased the weight for X to 0.8. These weights are passed into the training function, helping the model treat each class with equal importance and avoid bias towards more frequent classes. Next, for the load-based model, our MobileNet V2. At the heart of our model is MobileNet V2, which we load into with include underscore top equals false to remove the classification head. We use weights pre-trained on ImageNet and freeze all layers initially. This allows us to keep the powerful feature extractors intact while focusing training on our new classification head. Next, since we removed the classification head, we have to add our custom classification head. So we built our custom classification head. It starts with global average pooling 2D layer to flatten feature maps, followed by a 256 unit dense layer, then a dropout layer with a 50% rate to reduce overfitting. Then we add another dense layer with 128 units, another dropout layer, and finally a softmax layer that outputs one probability for each ASL letter class. This structure gives the model flexibility to learn higher level patterns while regularizing its complexity. So for the compile and train, this will be our initial phase. In the first training phase, we compiled the model with Atom Optimizer and a learning rate of 0.001. We use categorical cross-entropy loss, which is standard for multi-class classification. With the base layers frozen, the model focused on training only the custom head. This stage lasted for 10 epochs and gave the model a chance to specialize in ASL patterns without disturbing its core feature extraction. For fine-tuning our MobileNet v2, after the initial phase, we unfroze the top 10 layers of MobileNet v2 to allow some fine-tuning. This let the model adjust its deeper features to better suit the ASL data. We lowered the learning rate to 0.000001 to avoid catastrophic forgetting. We then trained for an additional 20 epochs, allowing for the model to gradually refine its feature understanding for more accurate classification. For predict and evaluate, once training was completed, we used the model to predict the classes of images in the validation set. To evaluate performance, we generated a confusion matrix that visualized which letters were predicted correctly and which were confused with others. We also printed a detailed classification report that includes precision, recall, and F1 scores for each class. These metrics helped us understand how well the model was performing overall and where it still needed improvement. And for save model and labels, we saved the entire model as an H5 file for future use and wrote all class labels to a text file. This allows us to upload the model later for testing or deployment and ensures that we have a mapping between output indices and actual letters. For visualizing misclassified images, we randomly selected one misclassified image and displayed it alongside its true and predicted labels. This gave us a clear visual sense of the model's mistakes. For example, if the model confused C with S, we could see it if the hand gestures were visually similar and understand the source of confusion. The final print statement confirms that the model and supporting files have all been saved successfully, wrapping up the training pipeline. To sum our project up, this project showcased a complete image classification pipeline using transfer learning. We started with a pre-trained model, added a custom classification head, and iteratively improved performance through data augmentation, weighting, dropout regularization, and stage training. MobileNet v2 proved to be a lightweight yet effective, outperforming cheaper alternatives such as ResNet 50 and earlier experiments. Most importantly, we learned how powerful transfer learning can be when combined with thoughtful tuning. This allowed us to achieve solid performance even with limited data. If we had more time, we would experiment with real-time gesture recognition, additional data sets, and maybe even extend it to full sign language phrases through video models. Thank you so much for listening.